All right, welcome back, guys. This is Anne-Marie Carrier from Herschel Jones, and we
Yay!
started our next live broadcast. We are going to be reviewing today chemical reactions and law of conservation of matter. I feel like we did a really good job of reviewing the periodic table and atoms, compounds, mixtures, and elements last week. So we're going to move on to this, and then we will actually have a session, if you guys are interested, on Monday night to kind of do a brief overview before the test on Tuesday. So if you want to attend, it'll be just a little bit of everything versus tonight being focused on one topic, okay?
Okay.
Let me get the chat boxes back open. All right, hopefully they'll be able to jump in now. All right, so let's go ahead and get started. I'm going to screen share with you. I'm sure I'm very tired after all those conferences this week. And I'm going to screen share, again, the presentation that I've created for you, just to go over a few things. It probably, I know I said this last time, it probably won't be as long as last time, definitely, okay? And so, and type in the chat box to the right, and I have a few questions for you so we can go over a few things, okay?
Alright, let me set up my chat room and turn off my mic. So long, America.
Okay. So let me know if you have difficulty viewing or reading any of this, because again, I know some of the text will be small.
Yeah.
Yeah, I'm sure on your phone, Colin. But I'll be talking and going over it, but we're looking at some equations today, so definitely those small subscripts. I'm not sure. You might have to hold the phone real close to your face. Okay. All right, so
Too close to look strange.
okay, chemical reactions and law of conservation online review. All right, so we kind of talked about this over the last week primarily, that chemical reactions indicate that a chemical change is going to occur. So we know back from our last unit, what does that mean is happening to the atoms?
They're changing.
Yeah, but are they changing on the
Hi,
inside
Jessica.
or the outside?
Hey, Jessica.
Are you gonna stay this time, Jessica?
Guys, are they changing on the inside or the outside?
There is Jessica.
Inside.
Okay, got it this time.
Try to stay focused, okay? Hi, Jessica.
Hey.
We just started, so you really didn't miss anything.
I have a crown.
How did you do that?
Okay, Emmanuel, we got to stay focused because we already started, all right? You can show her at the end, okay? All right, so anytime a chemical reaction happens, a chemical change is going on. It means something is happening with the atoms and molecules on the inside, and they're making something new. So I know tomorrow I'll be giving you back your chemical reactions lab, and a lot of people either didn't indicate that a chemical change was occurring when I asked was it physical or chemical, or they weren't able to really conclude that the properties of a substance totally change when a chemical reaction occurs, like before and after the reaction. Okay, and so we're going to look at that. But again, the properties are the characteristics. And most of the time, it won't look anything like it started if a chemical change is occurring, which means a chemical reaction. If it's just a physical change, again, we could have changes to the size, we could have changes to the shape, we could even have change to the state of matter, but that means that the atoms and molecules are not being affected in a physical change, okay? So in a chemical change or a chemical reaction, those should be kind of synonymous for you, okay? That means the atoms and molecules could be coming together to form a compound, or compounds can be ripped apart, and once they're ripped apart, those atoms can be rearranged in a multitude of ways to make an entirely new substance. Okay?
Okay.
All right.
Okay.
So we I did my amazing little demonstrations for you the other day. I hope you enjoyed them. And we kind of went over these signs. So again, if you see something or an example is provided for you that indicates one of these changes occurs, that means that something is happening with the atoms and molecules on the inside. Chemical change, chemical reaction. Usually you'll see smoke, fire, or light. We said a solid precipitate formed, which I don't know if precipitate is really the right term for what we did the other day, but okay, a solid was formed from two different liquid solutions, right? So that was kind of the sign or the change that I was looking for on our lab. Heat or temperature change, extreme change can occur, just like the skittle, which I know I still owe that demonstration to you, Jalen and Colin. It didn't work in our third period class. And then gas or bubbles are formed. Color change occurs, but again, some of you guys indicated that on the lab the other day, but what did we put in there to make it change color?
Food coloring?
Yeah.
The food coloring.
We just threw the food coloring in there, so there was nothing really magical about that. When you add color to something and it changes to that color, that's just creating another kind of mixture, okay? So, but I think what the example I used in class was, if you put bleach on something and it totally changes it to a new color that's not the color of that solution, then that would be kind of the color change that we're talking about. Also, sometimes when the gas or bubbles are formed, it might release an odor because it might be releasing an invisible gas that you can't see. But the big idea here is all chemical reactions, no matter what they are, is always a chemical change, okay? It's always changing the atoms and molecules on the inside.
Sorry, I didn't mean to do that.
Oh. That's all right. All right, so was that you, Jessica?
Yes.
Yeah, so on the Hangout, I had given everyone instructions before we started, but if you just search, like hover over the left-hand side, you should be able to open some of those special effects and kind of check it out as we're going, okay?
Yeah, I saw that.
I'll be happy to go over it with you a little bit when we're done. All right, we're not going to be long. So these are all pure substances, and they were all formed at one time from a chemical reaction because we know they're made of many different types of elements or many different types of atoms. So let's go maybe one by one and see if we can identify what elements and how many of them there are. Okay? So
I want to go first.
Okay, Emmanuel, pick one and tell me.
Wait, how many elements?
Hydrochloric acid is made of hydrogen and chlorine.
Okay, and how many of each, Emmanuel?
2.
Okay, 2 total or 2 each?
2 total.
2
1
total.
of each.
Right, 1 each.
Did I get it right?
You got it right. You picked the easy one.
I just chose the first one.
Okay, and is Gavin Superman?
Yes.
Okay, Superman. Why don't you pick one that you would like to do if you can see it on your screen and just tell me what elements it's made of and how many atoms of each, please.
Citric acid is made of hydrogen, carbon, more hydrogen, and oxygen.
Okay.
And there is 21 atoms total.
Okay, very good. That's exactly right.
Yay.
All right, awesome.
Yay.
Can I go next?
Somebody can applaud for him.
It's not the same as long, if you don't use Google Hangouts, you don't use the effects.
All right. Jalen, you want to try the next? You're next on the screen.
Okay. Okay, I can do it.
I know you can. Which one would you like to do?
Acetic acid.
Okay.
It has hydrogen, carbon, hydrogen, and oxygen.
Right.
And it has 8 total atoms.
Very good. That's exactly right. And acetic acid is the main ingredient in vinegar. Good job, Jalen. All right, Jessica, let's look up. Can you see the screen over your mustache?
Wait, didn't Jessica just go?
Oh, she didn't do this.
No, I didn't go yet.
Yeah.
Oh. I thought you went right after Gavin.
No.
Okay.
Hey, you want to try?
Yeah. I'll do sulfuric acid because it's right there.
Okay.
So it's composed of hydrogen, sulfur, and oxygen,
Right.
and it has 7,
Very
like total for all of them.
Right. And it's 7 what?
7 of each atom.
Well, 7 atoms, right?
Well, yeah.
Okay. And I know we're not done yet, but there's 7 atoms in one what of sulfuric acid?
There's 2 hydrogen, 1 sulfur, and 4 oxygen.
Okay. I was trying to ask everybody, like, that is right. There's 7 atoms, but
In
what's
one compound?
it is a compound. What's the smallest amount of a compound?
Molecule.
Molecule. Good. So that's what it is there's 7 atoms in one molecule of sulfuric acid. Awesome. I figured we might as well cover that. All right, and so this is Joel. Joel, you want to come out of hiding? Pick one for us.
Okay. Okay. See, since I'm on like a mobile device, the screen.
Okay, do you have a pen and a piece of paper? I can give you one.
Yeah.
Okay, tell me when you're ready.
I am ready.
Okay, write down H2CO3.
Is the O capitalized?
Yes. Good question.
Okay.
So it was H2CO3.
There are 2 hydrogen atoms
Uh-huh.
and 1 carbon atom and 3 oxygen atoms.
Very good. Very good. Exactly. So that's carbonic acid. That is the acid that is in the rain. When we say there's acid rain, that's what it is. That compound is mixed in to create a homogeneous mixture with the rain. So some of you actually use rainwater as an example for a homogeneous mixture in your foldable. That was awesome because it does have lots of stuff in it as it's coming down. Oh, Jalen, you look mighty special.
Happy birthday, Pirate Jalen. I am the king. I guess I pronounced you right. Pirate's
I
not.
can't see it. It's with the picture.
Okay, let's keep going so we can get done because we are halfway through already. Okay? And then Jolene, are you back there?
Yeah.
Okay, would you like to pick one that we haven't done yet?
Yeah, I'll do nitric acid.
Okay.
It has hydrogen, nitrogen, and oxygen,
Very good.
and it has a total of 5 atoms.
That's awesome. That's exactly right. Good job. And there are 5 atoms in
one molecule.
Very good. That's exactly right. Smallest amount of a compound. Y'all are going to be great on the test on Tuesday. All right. So, Colin, I know, are you having a hard time seeing the formulas?
Yeah, the screen is like messed up.
Okay. Can I give it to you, tell you what it says, and you can write it down?
Yeah,
All right. Tell me when you're ready.
I'm ready.
Okay. It's H2, big S, big O, 4.
Is the S small?
S is big.
Oh, okay. O and then 4?
Uh-huh.
Okay. I got it.
Okay, what do you think that's made of?
It's hydrogen.
Right?
I know it's made of oxygen, but I forgot what the S was.
Okay, somebody want to help him?
Sulfur.
Sulfur.
Good job.
That explosive compound that blows stuff up.
I think you're thinking of sodium.
Sodium's Na, right?
Right, but Emmanuel said it's explosive. I don't think sulfur is explosive. I think he was thinking of sodium being explosive.
It's mixed in gunpowder and then it becomes explosive.
Yeah.
Sulfur is?
Jalen, I do not know what to say about you.
He's what
He's
a
a
dog.
pirate at the beach.
He's like the cat in the hat, but with a dog and a goatee. Or whatever that is.
Okay. All right. So
I'll give you the clap.
so Colin, how many total atoms in one molecule? Please.
There's 7 in this one.
7. Very good. That's exactly right. Okay. Let's move on. All right. So we know that all of these chemical reactions, we can see what's happening to the substances by looking at their chemical equations. Okay, and the chemical equation always tells us, it represents what substances are going through the reaction and what's the product that we have at the end. Okay, so here, just like I had you guys count, we have hydrogen and oxygen that are going through the reaction, and what do we have at the end?
Our product.
Yeah,
Right, very good. And what is that thing what is our product?
Compound.
water.
Very good.
Water.
It's a compound of water. Good job, Jessica. So remember, I know Emma gave you the study guide today. It was asking about these numbers. Now, these were part of our vocabulary, so I wanted to quickly go
That
over
is
that.
finished.
You're finished?
Yeah.
Miss Carrier,
Yes, sir.
I didn't get the study guide.
Hi, Mark.
I passed them out at the end of class, Colin.
Oh yeah, but I was in the computer lab and I came by your class right before.
Oh, okay. Well, you can get it tomorrow, okay? Don't forget to ask me. It's actually in the
Nigel.
makeup bin already, okay?
Okay.
There's so many people here today, Miss Carey. This is so good.
I know. That's awesome.
Full house. Mark, we
You
cannot
guys-
hear you.
You must be good advertisements.
Yeah, come and join our thingy-mabob. It's really fun, and we get extra credit, right, guys?
Is that your word, Emmanuel? Thingy-mabob?
Yeah,
That's your
thingy-mabob.
slogan for to join our Google Hangout.
Yeah.
Whatchamacallit.
And remember, everyone, it's extra credit. Don't tell anyone else. It's a secret.
You keep telling everybody.
But they're already here.
All right. So let's finish up, okay? So we have the subscript. When it asks the subscript, who can tell me if you'll type in the box? Oh, that's kind of scary. If you'll type in the chat box what the subscript tells you about the compound.
Did I get it right?
Emmanuel, you got it?
Yeah.
Jolene got it? Very good, Jessica.
Skip me.
I don't see your answer. I'm sorry. Jalen, I'm sorry.
Oh,
I didn't leave you out. Good job. Good job.
All right.
All right. So what I'm seeing is that you know what the subscript is, but I had a lot of questions today about the coefficient, okay? Now, the subscript...
We all got it right.
Thank you, sir. All right, so the subscript always tells us how many atoms of a substance there are in the compound, like here, H2O. We know that one. We're very familiar with it. But the coefficient is always a larger number, and it comes before the formula, because it always tells us how many molecules of a substance we have. Okay, so if we have 2 H2O, 2 water molecules, how many total hydrogen atoms do we have? What do you think, Colin? If we have 2 H2O molecules. Any idea, Colin?
Gavin, you're really too close.
Mm-hmm. Colin, can you shake your head if you can hear me? Okay, are you thinking?
Turn the camera off.
Okay. So I don't know what you got going on, Colin, but we're going to move on, okay? So, Jalen, if you're behind there, can you tell me how many hydrogen atoms do we have in the water molecules? How many hydrogen? 4. 4 is right. So it's kind of like the distributive property. We have to multiply it times everything after it. Whereas sometimes if the subscript is outside the parentheses, then we have to multiply it in. Okay? So if you look on the left of this equation, we have 4 hydrogen atoms. If you look on the right, we have 4 hydrogen atoms. If we look back on the left, how many oxygen atoms? Anybody?
2.
2.
2.
2, yes.
2
Yes.
here.
Both.
Sorry, 2 here, right? The subscript. And then over here, how many oxygen atoms?
2. 1.
1.
2.
1.
1.
Okay.
Because it's
So-
2 H2O.
Right. So that's the idea, guys. Here there's 1, but because we have this coefficient and we have 2 water molecules, we have 1 in each molecule. So you would multiply this 2 times the 1. You distribute to the right.
I feel like we're in math.
Okay.
Math isn't science, and science as
It
well.
is.
And reading is everything.
You'll be doing a lot of math and science when you get to high school.
Especially when we have to start converting things from Celsius to Fahrenheit and the K thing. I don't know what the K thing is. It's just K.
Okay. So here's another example of a chemical equation. And again, we can count the number of atoms before and after. This is actually what chemical reaction would be between methane gas and oxygen. Like if you were burning it, do you remember if we burn it, what kind of reaction that's called?
Chemical reaction?
No. Yes? Maybe? I don't know.
Well, it is a chemical reaction because a chemical change happens. You can see the atoms and molecules have mixed up and moved around. But this is actually a combustion reaction. So methane gas is a flammable gas. It's made, you can see, of 1 carbon and 4 hydrogen on the left. Okay? Now we have to have oxygen present in order to have a fire. And we would have to have some catalyst or a spark or something like that. And so when it combusts, yeah, whoa.
Or that.
All right, when it combusts, guys, on the right-hand side, Jessica, can you tell me one of the 2 products on the right-hand side of our equation?
I think it's. Is it after the arrows that are?
Correct. After the arrow is what we get when it's done reacting.
No, it's carbon dioxide.
Right? We get carbon dioxide, and what else do we get, Gavin?
We get. Is that water?
It is water. Every time we have a combustion reaction, it doesn't matter if we're starting a campfire or burning gasoline or lighting a match. We still get some carbon dioxide and water, plus sometimes other substances depending on what we're burning. Okay? So the big deal here is that if you look on the left, we said we have 1 carbon, 4 hydrogen, and 4 oxygen on the left. Right? How many do we have on the right, Emmanuel?
You mean the 2 water molecules?
The total of all the atoms on the right-hand side of our equation, like in the products.
Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 6 plus 3, 9.
We have 9 atoms. How many of each?
2, 4 oxygen, 4 hydrogen, and 1 carbon.
Very good. And so you can see that the number and type of atoms, both the number and the type, in the reactants, the things going through the reaction, are going to be exactly the same as the ones afterward, right?
Yeah.
Okay. So let's look at some more. All right. Let's look at this equation. Jolene, are you still with us?
Yeah.
Okay, can you tell me in that first equation what elements there are?
Carbon and hydrogen.
Oh, which, are you looking at the same one I am?
Oh no, I think I was looking at the bottom first one.
Oh, okay, the second one on the bottom? Okay, so let's look at carbon. You say carbon and hydrogen, right?
Yes, ma'am.
And there's one more element.
Oh, and oxygen.
Right, carbon, hydrogen, and oxygen. So that equation only has those 3 elements in it. Again, it's a chemical reaction. So you can see that what we have in the beginning is different than what we have at the end. Jalen, what do we call the things that we start with in a chemical equation or a chemical change?
Reactants.
Very good. The things that go through the reaction are called the reactants. And what do we get at the end, Jessica?
The products.
The products. Awesome. That's exactly right. Okay. So regardless of the order, we still have carbon, hydrogen, and oxygen on the left. We still have carbon, oxygen, and hydrogen on the right. Let's see. That again, what I can't see. Oops, we lost somebody.
Oh no.
Mark, are you there?
Oh man.
Okay.
Yes, I am.
Mark, I can't see your face.
That's okay, but you just turned your microphone off. I was wondering if you could answer a question for me. You don't have to have your camera on to answer the question. But would you, in that equation, can you tell me how many atoms there are in the reactants? The second equation that Jolene just told us included carbon, hydrogen, and oxygen. You'd have to either type it in the chat box or you'd have to turn your mic on.
Can you hear me?
Yeah, go ahead.
Oh, yeah. I had a question. What was the question?
That's the question. Oh,
Yeah.
what is the question I was asking you? I'm sorry. I was asking in that second equation that Jolene just said is made of carbon, hydrogen, and oxygen. Can you tell me how many total atoms are in the reactants?
Okay. Just give me a second.
Sure.
$22? No, wait.
Oh, it could be 22 if you count all the way across. Sure could. That's good. I'll take 22 because there are... Okay, so let me go to that screen so I can point. Hey, when I move the cursor, okay, you can see that. Okay. So here we have 3 carbon, 8 hydrogen, and on this side we have 5 O2 molecules. So 5 times 2 is 10. So we're going to have 10 plus 8 plus 3, that's 11, right?
Right.
So we have 11 on this side, so what he did is he went ahead and counted all of these on the right-hand side as well. So we have 3 carbon, we have 6 oxygen, so that's going to be, again, 9. Oh, wait, did I count that wrong?
No.
Here we have 8 and 1 more. I don't think that's right.
That's right. We
Is 21?
no, wait, no.
Wait.
You know, if Gavin was actually paying attention and he heard you say 21, he would say it in that really weird voice.
21.
21.
Okay.
That's so fun.
Well, you know what? There are 11 on the left. Let's go with that. I mean, there are 5, 10, 21 on the left. Look, I am really tired. Did he say 21 and I only counted the left?
I think he said 20. I don't know. One of the two.
All right, Mark. Enlighten us. What did you tell us?
Yeah, I think that was 21 on the left. 21's on the left from what I counted.
21 on the left, and then there would be another 21 on the right.
Yeah.
Yeah.
21 on the right. Good. Because, again, we're looking at 3 times 1 for the carbon is 3. 3 times 2 for the oxygen here is 6. So we got 3 and 6 is 9. On this side, we have 4 times 2 is 8. And then we have 4 times the 1 oxygen here is 4. So that's going to be 12. And 12 plus the other 9. 12 here plus 9 here is also 12. Last I checked. Okay, very good. All right, so let's go back and let's see, Jessica, can you help me with the first one, the CaCO3? Can you tell us what elements those are?
I know there's oxygen, and I think that's carbon, right?
Right.
And
this is what's in your teeth.
is the Ca calcium?
It is. Very good. That's exactly right. And so, Gavin, do you think you can tell us how many atoms there are in, let's say, this whole side?
5.
Very good. There's 5.
Yay!
So, Emmanuel, how many are on this side?
It should be 5, but let me make sure to count. 1, 2, 3, 4, 5. Yay, it's 5.
Yes, very good. That's exactly right. And so,
I can count.
Jalen, can you tell me why? Can you tell me why or what says that these numbers have to be the same?
Because I know that both sides have to be the same because
there's a special law. Do you remember the name of the law?
law of conservation of matter.
Very good. That's exactly right. Law of conservation of matter, or the law of conservation of mass, and it tells us those numbers have to be the same. So remember.
Alright, what was that?
Thank you. Thank you very much. Okay.
Thank you very much.
So remember that what the law of conservation of mass and matter is saying, that none of us are able to create or destroy matter, that we can just change its form from one kind to another. So in a chemical reaction, when those atoms and molecules are getting mixed up, pulled apart, put back together, that's an example of the law of conservation of matter. We can't destroy it, but we talked about in class, we can make certain things unusable.
Like radioactive waste?
Yeah, well, it doesn't have to be radioactive. Radioactive waste suggests that there's material that's releasing harmful energy to the Earth, like the particles are breaking apart. When radioactive decay happens, Emmanuel, like an atom, it starts to lose its particles. The positive nucleus and the negative electrons, that attraction that holds them together, it starts to weaken. and it starts losing some of its subatomic particles. It releases them around the world.
But if it isn't that called alpha decay, and then it could also eventually turn into like another atom?
Well, it would, because as it loses some, it would turn into a smaller substance.
Yeah.
Okay, but you'll learn all about that in high school chemistry. Let's not confuse everybody for today. Okay, but what I want you to know is we can recycle things, meaning if we take plastic or aluminum or metal or glass and we put it in the recycle bin, that stuff's all made of matter, so we can take it and turn it into something else. So, make sure you know that during a chemical reaction, which is a chemical change, that the law of conservation of matter says that the type of atoms and the number of atoms have to be exactly the same before and after. Okay? Now, what I'm going to do real quick is I'm going to try to show you a little video that is essentially, I think it's the little brain pop that we did not watch.
Yay.
Yay, on law of conservation. Let me see what you see. Okay. So I'm going to jump back in. Everybody still awake?
Yep.
Yeah.
Hi,
Yeah.
Mark. Nice to see your hands.
I don't sleep.
Well, you
I
probably
don't need sleep.
Okay, I'm going to, if you,
What was that? I'm awake now.
okay, you probably got to turn your volume up, but your microphone off to hear it. But if
Okay.
you can't hear it, will you type in the chat box so that way I know something's going wrong? Because I haven't shown you a video yet. Okay? So we'll see if this works.
Mark, show me your face. Mark.
Yo.
Fix the phone. Let me see. I want to see you.
Okay, Emmanuel, you ready?
Yeah.
Okay.
Still trying to turn lead into gold? Hey, isn't this just food coloring? Dear Tim and Moby, what is the law of conservation of mass? And what happens if you break it? I love you, Marianne.
He messed up my name.
Thanks. You can't actually break the law of conservation of mass. It's not that kind of law. In science, a law is a generalization about how the physical universe works. The law of conservation of mass basically means that substances can't be created or destroyed. Or, in the language of chemistry, mass of the reactants in a chemical reaction always equals the mass of the products. Yeah, let's take a look at some of those terms. First of all, mass
Miss
is
Carrier, we can hear it, but we can't see it.
Yeah, none of us can see the image.
depending on how much.
Okay, but you can hear it. Okay, can
Oh,
you
there
see
it
it?
Oh,
goes.
it's that. It's
There
that.
it is.
All right, maybe because I full screened it, so let me go
Turn
back.
lead
I'm
into
sorry.
gold.
All right. Can you see it now?
Yes.
Okay.
Yes.
And do you actually send them a letter?
Hey, isn't this just food coloring? Dear Tim and Moby, what is the law of conservation of mass? And what happens if you break it? I love you, Marianne. Thanks. You can't actually break the law of conservation of mass. It's not that kind of law. In science, a law is a generalization about how the physical universe works. The law of conservation of mass basically means that substances can't be created or destroyed. Or, in the language of chemistry, the mass of the reactants in a chemical reaction always equals the mass of the products. Yeah, let's take a look at some of those terms. First of all, mass is the amount of matter a substance has. Unlike weight, which changes depending on how much gravity is present, mass stays the same no matter where you are. So, although you may have different weights on, say, the Earth and the Moon, your mass always stays the same. We're good? Okay, next. A chemical reaction is when two or more molecules interact to form different molecules. For example, hydrogen and oxygen react to form dihydrogen monoxide, or water. In that reaction, hydrogen and oxygen are the reactants, the substance that are around at the beginning of a chemical reaction. And the water is the product, or what's around after a chemical reaction takes place. The law of conservation of mass states that the mass of the reactants must equal the mass of the products. Well, I know it seems kind of obvious. Stuff can't just disappear or appear out of thin air. And before the law was actually written down, people had been proposing the idea for centuries. Probably the first person to propose the law in a scientific way was Mikhail Lomonosov in Russia in about 1748. But his work wasn't known outside of Russia until much later. In the 1780s, a French guy named Antoine Lavoisier came up with a more precise description of how the law works, so we usually think of him as its discoverer. Yeah, sure it's useful. If you only know part of the mass of the chemicals in a reaction, you can use the law of conservation of mass to figure out the rest. Let's say you have 4 grams of hydrogen and 32 grams of oxygen. By adding the masses of the reactants together, you can figure out the mass of the product, 36 grams of water. You can do it backwards too. Potassium oxide combines with water to form potassium hydroxide. So let's say you have 18 grams of water. How much potassium oxide do you need to get 112 grams of potassium hydroxide? Yep, you need 94 grams of potassium oxide. Yeah, you didn't use enough. It takes 250 grams of blue food coloring to turn lead into gold. Yeah, I'm joking.
I got all excited.
I mean, we need to send them a letter.
Well, sometimes people answer my letters. I'm trying to find the screen. I can't find.
Sometimes.
Did you really send them that?
Yeah, but I can't believe you messed up my name. Hey, you know how they said
brain pop.
You know how they said Lavoisier was the one who discovered the law of conservation of matter?
Yeah.
Well, interesting fact, he was a tax collector, but he liked science, and so supposedly he embezzled all this money, and they caught him while he was in the middle of all this work, and they sentenced him to death. And he asked for them to keep him alive for 2 more weeks so he could finish his work and his scientific discovery, and they said no and beheaded him anyway.
How rude.
Normal French people. Always kill everyone.
Or thousands of dollars probably in that day and age, but I thought that was interesting.
And the French kill everyone, and the Russians never tell anyone anything.
I don't know if you guys can see, but my mouth is dropped.
What?
I don't know if you guys can see, but my mouth has literally dropped.
Your
We
mouth.
cannot see you, Jalen. Your face is covered up by the clown and the cake and the monocle.
So they still headed him anyway? What's the point? Oh, God.
Hey, did you hear about the chemist who was reading a book about helium?
Oh, no.
No.
He couldn't put it down.
No.
Oh my god.
All right, let's get back to finish up the presentation. I think I got like 1 or 2 minutes.
Okay.
If I can get this to work, there it goes. All right. So here we go. So okay, listen, we're almost done. Okay, we got this slide and then just our little quiz game. Okay.
Yay, quizzes!
Yay, quiz game.
Quiz and then I have an example for you and then.
Mark, I love your thumb.
Then the quiz. So I'm not sure because I didn't look at the study guide in the last couple of days, but I think I'd asked you on there to come up with some examples of how the law of conservation of matter or mass and how that relates to things in the world around us. Make sure that you can explain that, okay, using some examples. So I want to go ahead and show you a couple on here. They just showed you one in the video.
And
we did the example in class with the water and the Alka-Seltzer tablet. Again, the way that hydrogen atoms and oxygen atoms come together in the same amount to make water. These are all good examples, but this is just another visual example for you. So let me pull this. Uh-oh, that's the wrong box. And it's hard to juggle all of these different screens. Hello, me again.
Ah, you're back. Oh, wait, who was that Miss Carrier's back? Who did that? Shame on you. Shame on you.
All right.
I give you that trombone.
All right. So, Emmanuel, you ready?
He's a little atom.
Okay. Yep, he's a little atom. His name is Adam. He says, the other day I was building the most amazing building out of blocks. I had a set of blocks that said 5 pounds of blocks on the case, and I used every block. So that means my awesome building weighed 5 pounds. As I was admiring my masterpiece, a horrible little creature, my mom says she's my sister, but I'm not so sure, she came and broke everything that I'd been working on. I was really upset. So I had worked so hard on that huge building, and once it was knocked down, it looked so small. I decided to see how much it weighed, and now that it was destroyed, I was shocked when I put all of the pieces on our scale. Guess what I found out?
It was 5 pounds?
What?
It was 5 pounds?
Yep. Even though my building was in pieces, it weighed 5 pounds, just like when it was a beautiful building. Who knew? So according to the law of conservation of matter, matter can't be created or destroyed. So even though that horrible creature destroyed my building, she didn't destroy the matter that made up that building. I decided to put this law to the test. And so she says, visit my links for the clay example, dissolving salt and snowman. So to see the law in action. We're going to look at the clay example real quick and see if we can kind of watch this. It says, can you see this? Because I don't see you anymore.
Yeah, I see it.
Okay. So it says, did you know that even if you change the appearance of matter, the amount will stay the same? It says, click on the arrows in the slideshow to read a poem about how clay can change. So, Jessica, can you read the little green screen?
Yeah, I can read that.
Do you want to read it to us as we go through so I don't have to read to you?
Yeah, I'd like that.
That'd be great. Thank you. Can you read that?
Did you hit the next button yet?
No, I wanted to read the beginning screen to start.
Okay, so does a ball of clay change weight when it is broken into smaller pieces?
He forgot the title.
It's okay.
Here we have a ball of clay. The number above is how much it does weigh. When broken into 3 smaller pieces to play, will it weigh the same as at the end of the day? Yes, the weight of the clay, the same it will stay, whether a big lump of clay or 3 small in a line they lay.
That was a beautiful rhyming thing.
No matter how you bend or break the clay, it will still weigh the same at the end of the day.
Oh, wow. Good.
Yeah.
Very good, Jessica. Thank you for your help. All right. So back to our real presentation. One more thing.
I want to read the next thing.
Okay. All right. So, Emmanuel, you're the perfect person for this job. All right. So now, looking at this slide, okay. So make sure on the study guide as well as for the test that you're able to give some good explanations of the law of conservation of matter in the world around us, okay? And then make sure also that you can explain why the equation at the bottom, why it is not a good example of the law of conservation of matter. So, Emmanuel, do you want to take a shot at that first?
Sure. What do you... Ah, no, sorry.
So why is the equation at the bottom not a good example of the law of conservation of matter? What's wrong?
Well, you have 1 carbon and 4 hydrogen, and the next thing you only have two hydrogen, and also you have 2 oxygen in the first one, but then you have 3 oxygen in the next one. So logic does not work here.
Okay, so what is that? What's wrong with it according to the law of conservation of matter?
You cannot add just add or take away atoms from somewhere from the equation.
Okay, Gavin, do you think you can elaborate a little bit more? I mean, he's right, but why can't we? What does the law say? Gavin, I can't hear you. Are you just pretending to be with us?
Sorry, my microphone was muted.
Okay.
Okay. So, if you do take it away, then it's against the law.
Okay. That's one way to look at it. How would it be breaking the law, though, right? Because the law says what?
That you can't take anything away or create anything. So
You can't create it or...
create it.
Or
It's the D
Oh,
word.
create it or destroy it.
Destroy it, right?
Yeah.
So, what happened here?
I
We
can elaborate.
destroyed them.
Okay, go ahead, Jessica.
So, since the law of conservation of matter, it states that it has to stay the same even if you change it. So, in the end product, the molecules have changed, and they're not the same as they were before.
Right. So, like you were saying, Gavin, we can't destroy them. So, there's 2 hydrogen atoms missing somewhere. We have to account for them. They can't just have gone nowhere. Even if they're by themselves, we would have to add them and say like +2 hydrogen by itself if it's by itself. This just looks like it disappeared. And then with the oxygen, it looks like we created one that we didn't have before. So we can't make an oxygen atom out of no oxygen atoms. Even the smallest particle, we have to account for everything according to this law. Okay? Now, one thing just to note, and I'll probably repeat this in each of your classes tomorrow, but when I asked about the law of conservation of matter on the chemical reactions lab, one thing is a lot of people put the law of conservation. We're going to find that there's multiple laws of conservation. In fact, Albert Einstein did a lot of work on the law of conservation of energy, which we're going to learn about next, and the law of conservation of matter, and he felt like they were almost 2 in the same, although they're 2 distinct different laws. So we got to make sure we're explaining which one it is that we're talking about. Just like when we talk about mixtures, sometimes we shorten it and we say homo and hetero, but we really need to use the entire word. Just like here, we need to make sure we describe the entire law. Okay?
Okay.
Alrighty then. Alright, so the only thing I have left is this little quiz that we can do, online quiz, if you guys would like to try it out.
Oh, yes.
Yeah.
All right, we'll see how we do. We're not going to be a millionaire today. I'll go ahead and pull up that screen.
Hey, my parents are home. Mark, what is that poster?
Oh, that's a painting.
Why is there a painting in your room?
This isn't even my room. This is just the hallway.
Why are you in the hallway?
Because my computer's like...
Oh my god.
Your computer's in the hallway?
Trouble explaining my house setup.
You could always just use your phone.
I am using my phone, like...
Your internet does not reach your room?
No, it does. I was just finishing the science study guide.
Okay. So, Emmanuel, why don't we do the quiz, and then you guys can call each other. So, Jessica, now that you know who's on here, when I stop the broadcast, which is recording and on our YouTube channel, you guys can call each other and do the same stuff and play and make faces and wear hats and all of that, okay? So let's finish up so I can go to bed because I'm old and tired. Okay.
You're not old.
I'm older.
Old.
Okay.
You're not old, you're just older.
Yeah.
Well, thank you. Thank you very much. Okay.
That still sounds kind of mean either way.
That's okay. I'm good with it. I think I look good for being old. So, all right. So you might have a hard time, those of you like Mark, on your phone because the typing, I can't make this screen any bigger. And it's on this little teeny screen. It says, test your knowledge. There's Adam again. He says, he didn't answer, sorry. He says, now it's time for you to test your knowledge. We're going to start the quiz, and then it's multiple choice. So what we did last time is if you have the text box open on the side, if you can answer there, I'll take the most answered option, okay? And I'll read it out loud. I'm having a hard time reading it. Okay, so we're going to get started. Let me pull the screen where I can read your answer. Okay. Here we go. Okay, it says, a student mixed 125 grams of sugar, 250 grams of water, and 5 grams of flavoring. The solution, which is the homogeneous mixture, how much would it weigh according to the law of conservation of matter?
This is why the world invented calculators. How do I add Jessica to my circles?
Honey, you'll have to wait just a minute until we're done, okay?
I'll have you afterwards. Just wait until afterwards.
Okay.
Thank you. All right. So the answer I got 75% of the time was 380.
Yeah.
So I'm going to click that and click check answer. You are correct. 125 plus 250 plus 5. We can't forget the little 5. That would put it from 375 to 380. All right, let's look at the next one. Sarah and Jake were each given a ball of clay of the same weight. Both students used all their clay to make an object. Sarah rolled hers into a ball. Jake made a long, skinny rope. What is the weight of the clay figures now? Sarah's weighs more because it's round. Jake's weighs more because it's long. There's no way of knowing, for the figures would be equal. I have 3 answers, just waiting for maybe a 4th. Okay. So everybody said they would be equal, okay? That is exactly right, because it said in the beginning that they were each given a ball of clay of the same. So it doesn't matter what they do with it, it's still going to have the same mass. And so I wanted to kind of look at this real quick. Remember how we said the law of conservation of matter can also be called the law of conservation of mass, because remember, every atom that something's made of has mass. So if it's made of the same amount of matter, it's going to have the same mass, or vice versa. If it has the same mass, it must be made of the same amount of matter, because that's what mass is measured, right? So that's why they're using actual measures for the mass here. Here's another.
Put it in your room.
5 grams of salt is dissolved in 100 milliliters of water to form a saltwater solution. The solution is heated and the water boiled away. How much salt would you expect to have left in the container?
Requires math.
This math is easy.
See, y'all are awesome. That is correct. 5 grams. And that was one of the processes of how to separate a solution, or how to separate a homogeneous mixture. You could boil it and the water would evaporate. Good job. All that's left is 5. All right,
Yeah.
the next one. Which of these will weigh the same after it's undergone a change? Paper being burned, sugar water being evaporated, two chemicals reacting to form gas. Ammonia added to steel wool to create heat.
I think so. The
E.
water being evaporated.
Two chemicals.
Paper being burnt.
That's a hard question,
No,
huh?
paper being
Two
burnt.
chemicals. Two chemicals.
Oh, so we got lots of different answers. I wonder if we can do more. You guys answered 3. Okay, we're going to try again. Anybody think it's ammonia added to steel wool to create heat?
Hello, I'm back.
What does the law of conservation of matter say about the chemical reaction?
It'll weigh the same afterward.
All right, so the answer should be which ones?
Two chemicals.
Sugar water.
I think it might be all of them. Let's try it.
But, well, yeah, I guess that would work for all of them, wouldn't it? Because they're all...
Yeah, it might be hard to catch the evaporated water. It might be hard to catch the gas, but essentially it should have the same. Let's see. Uh-oh.
Oh. But
I think it'll just be two chemicals.
when it's burned
Two
into
chemicals.
ash, it's still going to be the same amount of matter, just in different form. But then...
Yeah, but it wouldn't be in like that area, so it would have gone away.
I think it's sugar water. I still think it's sugar water.
Okay, they're going to let us move on, so...
We'll never know.
All right. It says, which shows that matter may be changed, but the weight will not change. Some papers weigh less after they have burned. A clay ball that's 5 centimeters long and then rolled into a snake 10 centimeters long. When comparing markers, 20 thin markers will fit in the same box as 10 regular markers.
Getting kicked
A candle
out.
that has only burned for 30 seconds should still weigh the same.
A candle.
It says, which shows that matter may be changed, but the weight will not change.
A
Can you
candle
read
turns
the
to
answers
liquid after you burn it.
please?
Yes. The first says, some papers weigh less after they have burned. A clay ball that's 5 centimeters long is then rolled into a snake 10 centimeters long. When comparing markers, 20 thin markers will fit in the same box as 10 regular markers. A candle that has only burned for 30 seconds should still weigh the same. I see that you guys got 3 have said candle. I don't like this question.
I don't like these
Try
questions
number 2.
at all.
I don't like a lot of these questions.
Probably the markers.
Try the second answer.
The clay ball.
The marker.
Oh, because the clay ball is, yeah,
It's-
the clay ball is still the clay ball.
Yeah, it's just in a different
That's what I don't. Yeah.
Okay.
Okay, there we go.
The
Yeah.
matter, well, I guess it can be changed.
15.
Okay, I think you can get this. 15 grams of vinegar will be added to 100 grams of milk. It thickens slightly. What does the solution weigh?
115 grams.
You're supposed to write it. You're supposed to write it, Gavin.
Yeah, whatever.
Not all of us followed the directions equally.
Add Gavin.
Well, there's something wrong with my text box. It'll show what I say, but not what anyone else says.
Oh, okay. Well, thanks for clarifying. All right, so that was correct. One more question. All right, Stuart measures 10 grams of water into a pan and then freezes it. A day later, he takes the ice cube out of the pan and notices it's larger than before. What will it weigh?
10 grams.
Impossible to know. The world shall never know. Now, I'm ready to take the kitchen of a Tootsie Pop. Let's find out.
10 is correct. Very good.
I'm a genius.
Yeah.
Awesome.
Yeah, for quiz.
Too bad there's no way to check your answers.
That's
Wait, hold on. Wait, we got that right?
You got it right.
Yeah!
All right.
not so hard. I felt the wind in my face.
So that's it for today's review. So what we're going to do is, again, on Monday, because it's the night before the test, we'll do this for the remainder of the year, pretty much the night before the test. We'll do like a 1-hour general overview if any of you want to attend.
It'll still be at 8 o'clock, right?
Yeah, I always try to do 8 so it's never too early before people are getting home and having dinner, and it's not too late that everyone has to stay up too late.
All right.
And of course, it's also being recorded, so it's going to be on our YouTube channel. Go back and review it, but at that point it'll be a little late. Also, Emmanuel and Jalen and Gab and Jessica, if you want to go back and look at the other ones that we've already recorded, so you can get that review, you are welcome.
Mute me, Jalen.
All right. So we are done for tonight. I am going to stop the broadcast, and you guys are free to call each other and have fun. Thanks so much for coming.
Jessica, do you want to talk right now? Stop muting people, Jalen.
I have to stop the broadcast, Emmanuel, so that way it will stop recording to our class. Okay? But then, Emmanuel, Jessica will find you. Okay, because she can find you in the side in the chat box now on her Google+.
Yeah, I think I added her. I figured out how to add her.
Okay. So thanks again.
Stop
I'll
it, Jalen.
this morning. Come and see me if you have questions with the study guide, and I'll see you in class.
All right.
Bye. Good night.
See you, dude.